Okay, so today I'm gonna talk about Poisson distribution. I never worked before with this distribution, so Nathan or João, if you have something to add, please feel free. Uh, so I did a short presentation, so maybe 30 minutes and we'll finish. So the Poisson distribution, I can put it in here. The Poisson distribution is a discrete probability distribution. So we use this distribution when we want to estimate how many times an event it's like to occur within the given period of the time. And this period of the time has to be a fixed interval. So like we use the discrete probability distribution when we are counting some events. So how many calls a call center receiver, how many vaccine shots people receive, how many COVID the person take. So use this kind of the distribution. So the Poisson distribution has a lambda that is the rate parameter that indicates the expected value of the Avenger number of events in the fixed time event interval. So basically, we wanted to estimate the lambda parameter. So the Poisson has a lot of prerequisites. So first of all, the distribution has to have the discrete distribution. So the dependent variable must be a count of events and never negative, because we don't count negative events. So makes sense, but sometimes it's better to say again. So this is the distribution. Oh my God, I forgot the name of this curve. It's a curve of the distribution. Will never be a normal distribution because we are counting events. So this is events we are increasing and then decreasing, or they can start really high and then decreasing. So will never be a normal distribution. And all these events has be independent each other. So they had not to be a dependent of factors. So this is the second prerequisite. So the Poisson distribution assumes that the events occur independently of one another and have a constant average rate. So like if I wanted to check how many calls a call center receive, the calls will not be dependent to each other. It's always independent events. So there has to be an absence of multicollinearity. And the most important is the equidispersion. Because the Poisson assumes that the variance is equal or proportional to the mean. So if I have a mean like equal to a variance, we have a good equidispersion, or the lambda has to be lower than 1.0. So when I found this, I have a equidispersion. So the variance and the mean, it's really difficult to be equal. So the closer they are, it's better. And of course, the sample size, because the smaller sample size, the fit of the model will not fit in okay. So basically, this is the more important prerequisites that we have to check when I'm working to a Poisson distribution. After we apply the model, we need to check the residual analysis, the super dispersion test, and the goodness of the model fits. So I'm really nervous because João is here. So, okay, I make,
I can leave if that's a problem. No worries.
yes, Nathan, you have a question?
It's more like a comment. For Poisson distribution, one thing that is important for us to check is either we have a lot of zeros, because this is a count distribution, you can count zero. How do I count zeros? I don't.
Yeah.
So we need to be aware of how many zeros you have, because otherwise you're gonna have to change a little bit the model to a zero inflated or something like that because of the amount of zeros, because it can really skew the distribution itself. So for Poisson, then sometimes if you try to get, if you have like 1 0, sometimes depending on the sample size and the echo-dispersion, the model may not run if you have only 1 0, because it will be a lot for the model. So it's something that we need to be mind about. It's just this that I wanted to share.
Yes. Thank you, Nathan. I think Obali?
Yeah, Lance, I just wanted to know the definition of multicollinearity in this case.
The predictors not to be a high correlation between them, because if the predictors you are addiction in your model, they can be, if they are correlationate, this is not the fit to the model well. I don't know if I explained correctly.
Yeah, you explained and I got it, but I'm looking at it more in the terms of how can I explain it? So is there some extent of collinearity that we would tolerate? That's kind of the question. But when they say absence of multi, what's the meaning of the multi?
It's because it is the same context, the collinearly. The motive is because the predictors has not be correlated between them. But I saw this context multicollinearly, but I saw also just collinearity. So I think it's the same.
Yeah, it depends on
Okay.
the number of variables you're including as well. If it's only one covariate, like one of the predictors there that is collinear, the correlation there. If you have more, for instance, let's say that for this number of calls per hour that Laís would be modeling with her outcome there, she's adding the number of people that are taking those calls, the number of inhabitants of that city or something. Depending on the number of variables, you would get either multi-correlated, I don't know the term, versus only one predictor. I guess that's the gist.
Okay, so meaning kind of that if we had collinearity just between two variables, we are good to go. But when we have 3 plus, we won't, something like that.
Yeah.
So, okay.
Well, kind of. So let's break things down here. Collinearity is the statistical term for when two predictors have a high correlation, meaning that they are collinear. They share the linear relationship with the outcome, right? And multicollinearity is when you look at that from a multivariate perspective. So you have more than one variable sharing a linear correlation with the outcome. So it does not mean that collinearity is good. It also does not mean it's bad. It means that collinearity or multicollinearity, when you're trying to fit multivariable models, is something you have to be careful about, because they could be hiding causal pathways, or they could be hiding confusion in explaining the outcome, and we want to be careful about it. And that's one of the reasons why when you're doing regression modeling from a predictive model perspective, then collinearity and multicollinearity are not that important. They're more important for the sake of parsimony. If you have two very highly related predictors, you might not need both of them to predict the outcome. But when you're doing regression model to predict the outcome, but really to try to estimate the most precise coefficient in that relationship, then collinearity and multicollinearity are very important because they're going to confound the other coefficients that you're going to find. Right? That's why you need to be careful about it. Does that help, Obali? It doesn't help you saying that there's a good path, because there isn't. The ways you address that, and maybe we can have a session just on that, is you can calculate a score called VIF, which is analogous to saying what is the level of importance that a variable has in predicting the outcome. And then you see how big the VIF is by excluding or not a particular variable, and that tells you how big the collinearity is in that particular outcome. And that's the way you inspect the model. But I want to run away from giving you a rule of thumb on where is good to go, because this is something you have to think about from a theoretical perspective of which variables you're including into the model and how potentially they are confounding each other. And then you look at it from a data-driven perspective by inspecting how it impacts the model. Okay?
Yeah, thank you for the explanation, Joao. I was indeed looking for that rule of thumb if I thought there exists one. So I think that it would be good, therefore, for us to explore multicollinearity in this sense, so that we get some kind of guiding principles, as you've explained.
Okay. So can I go? Okay. So I try to do some codes in R to show for you. So I make a question. So how is the number of COVID-19 infections in a population is influenced by the number of vaccination, age, and history of previous pulmonary infection. So basically, we are going to check in R the dependency variable should be not normal, check the mean and the variance, build the model, check superdispersion, check residuals and multicollinearity, and check the model fit. So let me. So basically, I don't have a data set with Poisson distribution, so I build one. So will be a really good data. So the results will gonna to fit very well to the Poisson model because it's a curated data set. So first of all, we have to check the distribution of the dependency variable, and we can see that it's not a normal distribution. So in here, like the Nathan was saying, probably we need to check the quantity of the zeros because maybe there's a lot of zeros in this model. So in here, we are not to do the zero inflated, so you are not to check this in here. So the second one, we have to check the mean and the variance. So if we look at the mean and the variance, it's really close. So this is a good prerequisites because we can see probably that it's not a super dispersion between the data, but we needed to check this one after. But in here, it's good to see that the both it's close. And then we can build the model. So basically, the Poisson distribution, we are going to use the GLM, like the linear regression, like the other distribution. So my outcome will be new infections, and then we are going to build the model with the number of vaccines, the age, and previous pulmonary infections. So we are going to choose the family Poisson, and I put the link log because I want to adjust the positive values in my results. When we see the result of the model, we can see that all the predictors, it has some significance in the model. So since the intercept, the vaccines, the age, and the previous infections. We can see that someone is negative and the other one is a positive, interfering in the outcome. So basically, after we build the model and we get the results, we need to check all the other prerequisites. So we can check the super dispersion. So when you see the results, so in the super dispersion model, we can see that it's 0.76. And if you will go back in here, we can see that to have a equal dispersion has to be shorter than 1.0. So it means that my model doesn't have a super dispersion. So basically this result, it's like, sorry, when you see the close results between the mean and the variance, we can see that they don't have a super dispersion. After we have to check some requisites of the model, like the residuals. So if you look at the plots of the residuals, the first one is the residuals against the fitted model. It's not perfect, so maybe it's because the high number of the zero. So probably we need to fix this model. But it's okay. And if you check the histogram of the residuals, it's almost a normality distribution, but it's also not perfect. And if you check the key plot, it's also not perfect. So because all these basic residuals plots has to be like the others distribution, like the gamma distribution has to be follow the same requisites of the other distribution. So it's not a perfect model. So most of the case, it's because the high number of the zeros. Then we need to check the multicollinearity. So it has to be lower than 10. So if you use this code, it's basically the package car. So we can use the VIF and the model. And here you can see that all the predictors, it's lower than 10. And like João said before, all they has like some proportion in the results of my model, because all day it's close to 1. And basically in the last one, this one I learned with Nathan. So we can see if the model adequacy, we can use this function HNP, HNP. So we can see in this plot, let me see if I can explain correctly. So all the points in this graph has to be inside these two lines. So if you have all the points inside these two lines, this is mean the model is good. So, but in here we have like 2 points outside this threshold. So this means that 0.02% of the model it's not fitting well, but it's okay because the model supports until 1%, Nata. I'm not sure if 1 or if 10.
It's 10 usually, depending on the sample size. So as the sample size goes up, you can
Increase
lower
this
a little
value.
bit.
Okay.
And then if the sample size is smaller, then you can put a little bit higher. but it should not be higher than 10%. So this is called a half normal plot. It's usually one of the measures for us to see if a GLM model is good, because as this is something that I learned with my professor of statistics. He used to say that residuals sometimes for GLM models will not behave as normal because they're not normal. Even if you try, and they're not going to behave. So we take this envelope and create like those margins of like it's like a confidence interval for these residuals where they can be inside, so to check if they're half normal. They don't need to be completely normal. They need to be at least half normal. So that's why we have points out of envelope that need to be checked to see if the amount of points out of this half normal plot are extensive, because if they are, there's like 50%, it means that almost 50% of your model is not even close to be adjusting. So it's something like that, to be in layman's words.
So besides the residual plot is not so good, the model in here show for us that the model is okay. It's good to be used.
Nice.
So
Laís, I have a question going back to the when you fit the model and you show us the summary. And okay, so here, for the sake of the template itself, okay, so not your presentation. So let's say you're taking this code and you're gonna make it something that we can use, someone that is fitting a model for the first time, using that. So one suggestion for that would be for you to add a section where you do only a GLM, a binary association, so the infections and the vaccines, for instance. So not a multivariate model, but focusing on the univariate association there. And so the person is able to see the difference between controlling for the other important variables versus only using your interested variable as well. So just so the person can see the difference. And the other thing is that we need to remember that the estimate needs to be exponentiated so we can understand the impact of the actual effect measure that we want to see. So here it's showing the logged version, and you would need to exponentiate the estimate in order for it to become an incidence rate ratio. And then you could understand how impactful your covariates are on your outcome. And that would be something that is nice for you to add as well, like a second chunk of code that would show, hey, so this is the interpretation, right? So you have here, oh yes, so you had that there. I'm sorry.
It's because in the final slide I put the interpretation and analyzing results.
Yes, so forget everything that I said. Just add the suggestion for adding the univariate association there. But sorry, thank you. Keep going.
Okay, Joe, but thank you. Then because I decided to show this just to show that the model is okay, and then we can interpret it and analyze the results. So basically, this is my outcome of the model. So my outcome is new infection of COVID-19. So I use the predictor, the vaccines, the age, and the previous infections, like infections. I created this one. I don't know why, but okay. So the results in here, we can see the vaccines, the age, and the previous infection has a significance in the model, but the vaccines, it's negative and the other one is positive. So we can interpret this one like, the results show that for each additional vaccination, the rate of new infections decreased by approximately 39%. So if we go back in here, what I did, basically, like João said, we needed to make an exponential of each predictor to see how much this influences the outcome. So basically, I created a new one. I forget the name. Quando eu crio novo, como eu chamo isso aqui?
Like a new object, a new variable.
Yes, I create a new object and then I make an explanation of this new object in a new one. And then I basically multiply by 100. And then I have the result for the vaccination in my outcome. So we can do this. I don't know if of course, there are easier way to do this, but I'm still learning our program. So I like to do all the step by step. So basically, we need to do this for each of the predictor that has a significance in the model, and then we have the result. So for the vaccines, we use like to do the explanation, this estimate, and then we just explanation this one, and then we have 39% of the vaccinates. If we increase the vaccination, we decrease 39% the number of COVID infections. But we can see the age in previous infections. It's a positive value, so this means that increase the outcome, the new infections. So for each additional year of age is associated with approximately 1.87% increase in the rate of new infections, and have previous infections, pulmonary infections, is associated with a rate of new infections approximately 2.81% of new COVID infections. So we can put the estimate, or we can, I saw different papers. Someone's put this one, someone's just put the p-value, someone put the standard error. So I didn't see like a pattern of how put the values in the Poisson. Basically, each paper show a different one, but basically the results, it's like the same, just this one that is different in each paper. So basically, it's this one, the presentation. I'm sorry about the English, and I'm sorry if I missed something about the Poisson model.
No, it's great, Blaise. Thank you. It's good that you showed on the last chunk there how to do it individually, because people can go in and take the value from the model and do it and get the interpretations. And there are easier ways of doing like a nice table, and of course this can be taken from other templates that we have from the code as well. And even João Ricardo shared some code that can be used to do get all of the incidence rate ratios there in the chat. Would be a code that could be used. And it's good that when you use some of these things, or you can even do it manually, you can also get the confidence interval for that measure. There you showed us the standard error. So the standard error is going to be used to get you this, okay, in average, the incidence rate ratio for COVID or new infections decreases by 39%, but then maybe this ranges from 35 to 41, I don't know, based on the standard error, and could be helpful. If you want to test it out now, you just need to change the model object there for the name of your model, which I think it's model, the object that is called model. But then again, you can run this later and test it for if it works.
Mm-hmm.
No pressure right now.
So Liz, the only thing I joined a little late, so I didn't know if you mentioned at the beginning, but the other thing that's very important in a Poisson or any kind of count model analysis is that it's always constrained within a time. There's not any count, but it's count over a particular period of time.
Mm-hmm.
And in our explanation, I didn't get what the time period was, but that's why we get incidence ratios in the end, or incidence rates, if you don't make it a ratio. Thank you. Or instance ratios if you then create a ratio out of it. So it's always the incidence, which is the number of new events in a given time. And for that, you should calculate that. And what I wanted to get with this is that a generalized linear model is called a generalized linear model because it's a generalization of linear models. And so what we do is we take all types of data that are not continuous that you would be able to model with a linear model, and you generalize them, meaning you transform them into a continuous scale that then you can analyze in a linear approximation. So for binomial data like logistic regression or any kind of binomial related estimation, what we're modeling is the probability of an event happening. And it's a yes or no, but then what you're modeling is the probability, which now becomes a number we can analyze in a linear way. The same thing for counts. What you do is you analyze this number of events per time, per person time in your distribution, which now also becomes a numeric variable you can analyze in a linear way. So that's what the generalized families will do. And it's important to mention that because that kind of triggers how you interpret the incidence. So Poisson and other count models are always going to be tied to the time frame. And all of those assumptions you're making are related to the time frame you're analyzing as well.
Thank you, João.
Cool. Okay. So I couldn't join the past 2 weeks. What have we covered? Did we cover the other GLMs?
Not in the past 2 weeks. In the last week, Nathan presented us a methodology on spatial analysis, the SAT scan for case control mapping. And the week before, we talked about, Natalie presented to us about the Getty's or G statistics, doing that in R. So more of spatial modeling. I guess this is the first presentation on the templates that we were talking about on the GLM templates. And you guys can correct me if I am forgetting someone.
Cool. Oh, that's fine. Let's use this presentation to kind of center down around a structure for the analysis template that we can use for the other ones. So, Laís, if you could share your templates around with this group, then
Yeah,
we can
sure.
always take some time to comment on them, and then we can use the next week's meeting by the end of it or by the beginning. Let's take the end if we have some time left. Just circle through edits and comments we want to make on the analysis template. And then we go to the next round, which is thinking about a writing template for this. Okay. Cool. Great. So please circulate that. If you could, and if it doesn't work for you, the timeline, that's fine. We can do it in another session. But if you could put together a very simple template for reporting Poisson or count-based models in methods and results that we can circle through. Again, it doesn't have to be next week if you're not ready, but I want us to start circulating back to the methods that were presented, which ones we're transforming into templates, and if we're really working on it to get us moving. So yeah, that's great. And then